In this video, we're going to look at input impedance and the motivation behind it. Sam, please describe the normal circuit's motivation explanation of what we see as input impedance.
Yeah, so, back in second year, when we're confronted with very complicated circuits, you might not always want to consider the entire chunk of circuit, right? You sometimes want to simplify it into some sort of input impedance. You deal with all your series and parallels and add them together, then you get a single number to deal with, a single circuit element to deal with. Can we do the same for transmission lines?
Well, we start out with some source that'll drive the transmission line, and the transmission line will send the energy down to the load. So what do you think, Sam? Can we model the impedance, input impedance?
I guess so, yeah, but I don't really know how to get around doing that. Can you enlighten us?
So let's start. The input impedance is the voltage over the current at some reference point. So we're looking into the line to simplify the effective impedance seen as you're looking down towards the load through the actual line. So let's do it. So we have a forward traveling voltage. So let's just do that. V naught plus e to the minus gamma z. And gammas, before I'll write it down when we're done, is going to be J beta. Okay, V naught plus, so that's the voltage. And the current, of course, is V naught plus over Z naught times e to the minus gamma z. So, by the way, that just looks like Z naught. So, but we have a load. What do you think, Sam? Does that look okay?
Let's step through this. I guess if you have a forward wave coming in at the source, the wave would travel forward until it hits the load. And if the load is the same as the line, if Z load equals Z naught, then it gets absorbed and it's good. But what if it's not?
Yeah, so if ZL is bigger than Z naught,
then you get some reflections.
So anytime ZL is not the same as Z naught, we're going to get reflections, whether it's bigger or less. So we got to add some
backward
terms.
waves.
So let's add a reflected wave. Go ahead, tell me what the reflected wave should look like.
Okay, V naught minus for the
That's the
backward
amplitude,
direction, and then e to the gamma z.
E to the plus gamma z, because the wave is going in the opposite direction. Let's write down, in this case, we're dealing with lossless line. So gamma is J beta. And now what about this term? So I'll start writing it down. Plus, same idea, divide by Z naught, V naught minus over Z naught times e to the gamma z. And now...
Wait a minute, isn't it minus?
Oh, minus. Yeah, we forgot. That's got to be the most important thing. Minus. Don't forget that minus sign. So now, we're all set. Here's our wave impedance or our input impedance. They're the same. It's a wave effect. The effect of the load is seen in this reflected wave amplitude, which is some fraction of the incident wave. And now you can see that the input impedance, also called the wave impedance because of the wave effects, depends on where you are along the line. So this is very different from circuits.
So if we cut the line here, you might see a different input impedance than if you cut the line here.
Absolutely.
Or here.
So that can be used to do diagnostics of the line, and we're going to look at the effects of studying this in a graphical setting for the lossless case.
Great.